Hello and welcome to this lecture. We're going to continue looking at applications of these symmetric matrices in various systems, modeling and all that. And one of the nicest applications is this oscillation modes in systems. So, quite often you have, it could be a mechanical system with a lot of springs and masses attached, and when you displace the masses will start oscillating. And it can also be an electrical system where you have capacitors and inductances in various coupled circuits, and then if you charge up one of the capacitances, then it will start oscillating with the inductance and all that. So all these oscillations show up quite often, and you can take a musical instrument, you excite it at one end, it starts producing standing waves and various modes. So various physical systems out there are modeled as supporting oscillation modes. So this is a very crucial idea. It cuts across all engineering. Even in chemistry, when you look at molecules that are connected to each other or have forces of attraction with each other, the basic model is that the molecules are oscillating a little bit and the modes of oscillation enter the picture. So all of these things are captured by differential equations usually, and when they are coupled, there is a decoupling that you can do with symmetric matrices. So I'm going to show it in a very simple example. Of course, there are more complicated examples of this in other areas. Okay, so let's get started. We are in electronic system, so we will start with the electronic system oscillator, which is this basic LC oscillator. You might have seen it before, but I want to show you real quick how this oscillations occur in these kind of things. So there's various physical ways to see it. The charge in the capacitor will result in a current, and that will result in a voltage across the inductor, and then that current will fall down, and then it will increase again, it will end up charging the capacitor. So all these kind of physical ideas can be written down, but a nice way to see it is mathematical equation, right? So you have here an inductor and a capacitor connected in series in a loop, right? This has various names associated with it. The inductance I'm calling L, the capacitance is C. The voltage across the capacitance is Vc of t, Vl of t is the voltage drop across the inductance, and the current is flowing in this direction to make sure the signs will work out consistently. Okay, so this is the basic LC oscillator as it's called. Okay, so what is our equation now? This current and the voltage across the capacitance are related, right? So that's the first equation I'm going to write. This I of t is going to be C times Vc prime of t, right? So this is first equation, easy enough to write. And then next, once this current starts varying through the inductance, the voltage will develop there, and that will be related as VL of t equals L times I prime of t, right? So this also we know. Now I of t already has been written in terms of Vc of t, so let's plug that in here. So if you plug this into this, you're going to differentiate again, and the C also appears. So you see VL of t is LC times Vc double prime of t. Okay, so I've got VL of t here in terms of Vc of t. Now we can do Kirchhoff's voltage law, which is this around the loop the voltage has to be 0, right? So that's VL of t plus Vc of t is 0, and instead of VL of t we can plug in this guy, and we finally get this nice looking equation which only has Vc of t. So LC times Vc double prime of t equals minus Vc of t. So this equation is the controlling equation for this little circuit here, or this little system here that we have. You have this. So now this kind of an equation occurs in mass and spring systems, in chemistry, in molecules, in musical instruments, here, there, everywhere, right? So anywhere you see oscillations, sine waves, tunes, music, vibrations, anywhere you see these things, this kind of an equation will show up. Okay, so this is a very basic oscillation equation. Double derivative equals minus the function. Okay, so that is the basic idea that gives you a wave equation, as they say. Okay, so now how do we write this down? So this is usually written like this. Okay, so for a system like LC here, we will define what's called a natural frequency, which is omega naught square is 1 by LC. See, this LC will come down here, and you'll get a minus 1 by LC here, right? So that 1 by LC we will write as omega naught square. Why omega naught square? Why this? Why that notation and this? You'll see soon enough when I tell you the solution of this equation. But this is a very standard way in which this equation is written. Okay. So now it turns out the solution for this is quite obvious, and you know this function, and if you plug it in, you'll get the answer, right? So we know that when you do derivatives, the sine and cos don't change, and of course the constant comes out, and the omega naught square is working very nicely here to quickly by inspection. This you can also derive using various methods, but just by inspection you can see that a solution for this equation is sine omega naught t. So that's why this is called a wave equation. So if you can somehow magically in your system create a variable which satisfies an equation like this, you will be producing sine waves. Your system will be oscillating. Okay. So the second order equation here has the sine omega naught t as a solution. It can also be cos omega naught t. It can also be various other forms. In fact, the most general form is maybe something like this: a sine omega naught t plus phi. Okay, where this a and phi, these are additional numbers that appear, and they have to sort of satisfy some initial conditions here and all that, so you can make it work. Okay, but I will not use this more complicated formula. I am happy with sine omega naught t. That's a solution that fits me here. Of course, in a physical situation, there may be slight variations in phase and amplitude. You can adjust for that. Okay, so this is a wave equation, and this is a solution for a wave equation. Seems simple enough. So in fact, so like I said, any system, not just an electrical system, it could be a mechanical system, chemical system, vibration system, this, that, wherever. If you get an equation like this is called a wave equation, and this means you have sinusoidal oscillations occurring at what is called the natural frequency, which is in this case root of 1 by LC. Okay, so this is a basic LC oscillator. This is a basic fundamental oscillation mode. There's only one frequency in the oscillation, nothing else is happening, right? So this is LC oscillator. Now what will happen frequently in more complicated systems, more complex interactions will happen, and you will have couplings. Okay, so these LC oscillators may be coupled in this fashion. Okay, so even in springs, if you have one spring and a mass connected to a wall, that's just one oscillation. But this mass may be connected with two springs, or maybe there may be two masses and three springs. They may be connected at the edge, and you may start oscillating. So it's easy to couple these kind of oscillating systems, and their energies can be shared and all that, and you may have more complicated modes of oscillations happening, right? So if you have, just imagine the mass and spring system, if you displace one of the masses, it will start oscillating, and then that oscillation will induce an oscillation here. So energy gets transferred between these systems in complex ways and goes up and down, and it's very interesting to study such systems. So one such system in the electrical setting is this one. Okay, so this is called the coupled LC oscillator. Okay, so I have an LC oscillator on this side. I also have an LC oscillator on this side. Instead of leaving them alone connected by themselves, I am going to connect them to each other through a capacitance which is now C1. Okay, just to keep that capacitance different. In general, this could be different, C1. Okay, so just a warning, these kind of ideal circuits are difficult to realize just with inductance and capacitance, because then wires will have resistance, things will wind down, etc. All of those things will happen. So, this may be an ideal picture, but like I said, it's used as a model for various systems. So it's useful to study these things. Okay, think about it like that. So you have an LC oscillator here, LC oscillator here. They are coupled through this coupling capacitance C1. Okay. Now let's start looking at this from voltage and current point of view. I'm going to mark the voltage across this capacitance plus minus like this. This capacitance also plus minus like this, so that the current I can think of as flowing in this direction I1, current is in this direction I2, and then the third, this coupling capacitance I'll put the other way around, plus minus and I3. These signs are arbitrary, you can do whatever sign you like. I'm just doing like this so that it works out in some way. So current flows like this, the capacitance voltage across the inductance will be like plus minus in this way, plus minus in this way here. So it just will naturally work out, and I'm writing like that. Okay, so but these signs are arbitrary, like when you solve circuits. So this is the thing. So now the thing is, if supposing you started with some charge on these capacitors, so how is it going to evolve, right? How are the charges going to oscillate? There will be oscillations, as you can imagine, but how are the oscillations? What are the modes? Okay, so you may guess that omega naught equals 1 by root LC is one mode, but is that the only mode? There is some exchange of energy going on between these two oscillators, right? So maybe some other modes may happen, right? So how do you write this down as an equation? And where is the symmetric matrix going to come into this picture? So you'll be surprised the way the symmetric matrix will enter the picture here, right? So let's see that. So the first equations are very easy to write down. I1 is C V1 prime, right? I2 is C V2 prime, and I3 is C1 V3 prime. Okay, so that's just the current equation through the capacitance. Okay, so now we also have Kirchhoff's current law here, because there are two currents adding to give a third current. So I1 plus I2 equal to I3. So I'm going to do a little bit of manipulation here with some sort of an approximation to translate this current equation into voltage, right? So if you notice, I1 is C V1 prime, I2 is C V2 prime, and I3 is C1 V3 prime. Okay. So now I can integrate from 0 to some t and assume that at 0 everything is 0 and then something happens after that. Just do a little bit of an assumption to get to an equation like this. Of course, you may have some constants here, etc., that will only unnecessarily complicate it, and I'm going to forget about those things and just write this equation as this. So I'm going to assume by integrating that my voltages satisfy this relationship. There is this alpha here. How did that come from? So notice here, if I integrate, I'll get V3 of t, V2 of t here, V1 of t here, and the C1 will go in the denominator here, and I'll get a C by C1. And that C by C1 I'm going to call as this alpha. Okay, that's just a parameter notation. So V3 of t is alpha times V1 of t plus V2 of t. So this equation satisfies, this circuit satisfies an equation like this. This comes from Kirchhoff's current law. Then you also have Kirchhoff's voltage law, right? So for these two loops you can write that. So you see, if you go through this loop, okay, the first loop here, you're going to get V1 of t plus L di1 by dt, right? But what is L di1 by dt? We saw it before. If you differentiate this, you're going to get C LC V1 double prime of t. Is that right? So this expression here is nothing but the voltage drop across the inductance. Okay, so L times I1 prime, but L times I1 prime is the same as C V1 double prime, because that's I1, right? So you see, we got this before. Plus, but then those are not the only two voltages in the loop. You also have V3 of t. So plus V3 of t is 0. So likewise, if you write the other way around in this way, if you go through the loop this way, you get V2 of t plus L I2 prime. Now I2 prime is C V2 double prime. So you get this equation. So this is the potential drop across the inductance L here. Okay, so you get these two equations. So now we can put all these equations together. I have an expression for V3 of t in terms of V1, V2. I have here two differential equations. So I can plug in this V3 of t into each of these equations. If instead of V3 of t, I can write alpha times V1 of t plus V2 of t. Even instead of this guy also alpha times V1 of t plus V2 of t, I have two equations in the two unknown functions V1 of t and V2 of t. So that's what I'm going to write finally. Okay, so now this LC is showing up and I know my natural frequency is LC. So I'm going to let this omega naught square be defined as 1 by LC. By the way, this equal to with the triangle on top is basically definition. I'm defining this new parameter to be like this. Okay, so 1 by LC. So once I do that, I hopefully you see that once I plug this in here and then move this around, I will get two equations like this. I'll get V1 double prime of t equals minus 1 plus alpha omega naught square V1 of t minus alpha omega naught square V2 of t, and likewise for the second equation. So I have two equations here. So now compare with the simple LC oscillator. In the simple LC oscillator, we got V double prime equals minus omega naught square V. There was only one unknown and one unknown voltage, and its second derivative was equal to minus omega naught square, its old value. Okay, but here notice what happens. You almost have that here. You have V1 double prime equals minus something into V1, but that's not all you have. The coupling enters the picture, right? You have minus another term into that coupled V2 guy. Okay, so likewise even for V2 double prime, you have some minus into V2. Okay, that's all right. But then the V1 enters the picture and it couples. So if these coupling terms are not there, then it's very easy. Okay, the problem is very easy, but then the coupling terms are there. Okay, so you have sort of like a matrix type picture here, but and the coupling terms, and you can see that the coupling terms are both equal, right? Minus alpha omega naught square minus alpha omega naught square. So you should start smelling the presence of a symmetric matrix here. Okay, and when you have a symmetric matrix, you know that there is orthonormal diagonalization, and when you have orthonormal diagonalization, you may be able to get rid of the coupling term. If you get rid of the coupling term, maybe these problems can be solved. Okay, so the same principle comes here again. The coupling enters the picture and you decouple with symmetric matrix. Okay, so let's see that slowly. But for now, this coupled LC oscillator system obeys these two differential equations. These are differential equations for the two voltages V1 of t and V2 of t. If you can solve them, you have solved the coupled oscillation. You would have found out what mode there is. And for solving, it appears that this coupling is a problem and you have to figure out a way of how to decouple. And there, symmetric matrices may help you. So here is where symmetric matrices come in. So for that, we are going to move from the differential equation world to a symmetric matrix equation. So you have two equations here. I'm going to write it as one equation involving matrices, and this is how I do it. Just check whether this is correct or wrong. It's easy enough to do. I will think of these two guys together in a matrix. Now you may argue that this is a function, this is a function. Don't worry about it. Just think of t as one particular value. Then this becomes a matrix, right? So it's like a matrix of where the components of the matrix are two functions. But anyway, the t is just a time variable. For every t, this has to be satisfied, right? So I can write like this. So I write a matrix here: v1 double prime of t, v2 double prime of t equals. So I've written here something to in just a simplified form. I've taken the minus omega naught square common out, okay, so that I will only get a 1 plus alpha alpha, right. So 1 plus alpha multiplying v1 of t plus alpha multiplying v2 of t, the whole thing multiplying minus omega naught square. So likewise in the second equation, this minus omega naught square is common outside. I have alpha times v1 of t plus 1 plus alpha times v2 of t, okay. So notice how a differential equation, set of two differential equations, became one nice vector equation, and that happened because of the linearity here, right. So there is no v1 square term or ugly term here, just v1 of t, v2 of t, it's just linear here. So in linear things you can write like this. So once you write like this, you see the differential equation, you see the symmetric matrix, right. So there is differential equation, when you convert to matrix, you see the symmetry here. This is a symmetric matrix. So notice how symmetric matrices enter into systems that originally you may not even think has anything to do with linear algebra. Suddenly the symmetric matrix enters the picture. So once I have a symmetric matrix, I can think of diagonalization, orthonormal diagonalization. So when I do orthonormal diagonalization, maybe I will get rid of this coupling terms alpha, right. These coupling alpha terms were the ones that were preventing me from using the direct solution. But if I can get rid of them by orthonormal diagonalization, then I am in the game. I can try to solve this problem. So how do we do that? To do orthonormal diagonalization, we have to find eigenvalues, eigenvectors. And the eigenvalues, eigenvectors here are particularly simple. You can easily add it, right. So if you see, the row sums are the same, right. So row sums are the same. So 1, 1 has to be an eigenvector, and the corresponding eigenvalue is nothing but 1 plus 2 alpha. Okay, very easy to identify one eigenvector and one eigenvalue. The other eigenvector, in this case, you can also see it quickly, or you can solve it if you want. It's 1 minus 1. In fact, that has an eigenvalue 1. Okay, so you can see 1 minus 1 simply gives you 1 minus 1. So what I've managed very easily to do with the symmetric matrix is managed to find an orthonormal. Of course, this is not orthonormal, this is orthogonal, but I can divide by root 2 to make it orthonormal, right. So what will be my orthonormal matrix? 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Okay. So the orthonormal decomposition for this symmetric matrix works out like this, right. So 1 plus alpha, 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 1 plus alpha is, the diagonal matrix is 1 plus 2 alpha and 1. Those are the eigenvalues. And then my my S matrix that comes here is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Curiously enough, this is orthonormal, but it's also symmetric. Okay. So its transpose, which will be its inverse, is the same. Okay. It's one of those curious orthonormal matrices which are also symmetric. So the transpose is equal to itself, and the transpose is also its inverse. Okay. What a strange matrix, right? So it's a very simple matrix here. It's symmetric, it's orthonormal, it's unitary, it's it satisfies all sorts of properties, and it's equal to its inverse. Okay. So I have now managed to get rid of the zero, the off diagonal element, right? This alpha has become 0 here, but I have this orthonormal guys multiplying, but that is not a big deal, right? I know I can do a change of variable to take care of that. Okay. So that's what we're going to do next, right? This is the decoupling by orthonormal diagonalization. That's also very important. Okay. So you have v1 double prime, v2 double prime equals minus omega naught square, and instead of 1 plus alpha, 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 1 plus alpha, I have written it in terms of the orthonormal diagonal decomposition, which is the orthonormal matrix multiplying by the diagonal matrix, again another orthonormal matrix coming up here, then v1 of t, v2 of t. So now we are in a very familiar world. So what I am going to do is, I am going to take this multiplication. So I am going to move this guy to the left side. Okay. So that you can do, right? You have to multiply both sides by the inverse of that matrix, but the inverse of that matrix is equal to the transpose of that matrix, which is itself. So you multiply by the same matrix on this side, you get this equation. So now you see this product here and this product here suggests a change of variable. What is the change of variable? I am going to change my variable to u1 of t and u0 of t. u1 of t is the first row here, so 1 by root 2, 1 by root 2 multiplying v1 of t, v2 of t. You get this equation, that is u1 of t, and then the second one multiplying here is u0 of t, which is v1 of t minus 1 by root 2 v2 of t. I have just done this multiplication. I have multiplied these two matrices together, right, and I have written the two entries as u1 of t and u2 of t. Okay. Now interestingly, what will happen when I do this substitution, what will happen if I differentiate this twice? If I do u1 double prime, I will get the same constant staying and v1 double prime, v2 double prime. u0 double prime will also be just one, same constants will stay, v1 double prime, v2 double prime. So this equation in terms of u1, u2, u1, u0 and u1 double prime and u1, u0 double prime becomes simply this equation, right. So you get exactly the same form here. So u1 double prime of t, u0 double prime of t is minus omega naught square times 1 plus 2 alpha 0, 0, 1 u1 of t, u0 of t. Note this little bit of magic here. I have gotten rid of the off diagonal element here. Okay, so initially I had that alpha and that was preventing me from solving it. Now I have gotten rid of it and now I can solve this. The reason is you just multiply this out and write it. This equation is nothing but u1 double prime of t is minus omega naught square into 1 plus 2 alpha times u1 of t, and then u0 double prime is minus omega naught square into u0 of t. Notice how the eigenvalues of my matrix alpha 1 plus alpha enter into the fundamental modes of the frequencies. So quite often the eigenvalues are associated with the frequencies, with the oscillation frequencies, the fundamental modes of systems. So that's very, very important to understand. Okay. So here is the two differential equations. These equations I know how to solve. This has no cross term, right? There's no cross term between u1 and u0. They're separate. I can solve them. My u1 of t is going to be sine root 1 plus 2 alpha omega naught t. u0 of t is going to be sine omega naught t. And from here I get two oscillation modes for my coupled LC oscillator. I have my original omega naught plus that's not the only oscillation mode. I also have a square root of 1 plus 2 alpha omega naught. Okay, so whereas alpha was my C by C1, right, the ratio of the two capacitances, and omega naught is 1 by root LC. So notice how wonderfully the symmetric matrix is entering the picture and helping you really understand what the solution is and how the eigenvalues become the fundamental modes of oscillations of a coupled system. Okay, so this is also very important. Okay, so here is a plot. I think quite often a plot is nicer to see. Now I showed you that u0 and u1 were sine omega naught t and sine root 1 plus 2 alpha omega naught t, but of course v1 and v2 are 1 by root 2 times u0 and u1, right. Of course this plus minus here, it's okay, it's all right. So here I have plotted with omega naught equals 1 this plot, and I am going to vary alpha here. So if you set alpha to 0, you notice that v2 of t will become 0, that mode will be absent, okay, and only v1 of t will be there, and that will be only omega naught. So this is my fundamental mode. Okay, I have only omega naught if alpha is 0, that there is no coupling, right. So basically there is no coupling at all. So this is that couple is like a short circuit, that capacitance, so it just keeps oscillating separately. Now as you slowly increase the alpha, increase the coupling, notice what's happening here. Do you see what's happening? Is I think it's better to see it larger alpha. When alpha goes very large, the one frequency, fundamental frequency omega naught will be visible to you. On top of that, you will get the other frequency, the root of 1 plus 2 alpha. So for instance, if alpha equal to 1.5, right, alpha equal to 1.5, you will have two frequencies. If alpha is 1.5, you have omega naught and 2 omega naught, okay, and adding and subtracting. If you subtract and add omega naught and 2 omega naught, you will get a picture like this. So this is two modes, omega naught and 2 omega naught. You can also go to alpha equals 5 by 2. 5 by 2 will give you, omega naught and 3 omega naught. Okay, likewise you can keep increasing, you will get larger and larger frequencies. So when you go to very large alpha, what will happen when you go to very large alpha? Omega naught is there, the same omega naught, and then on top of that is a very large small frequency. So it will add on top of that or subtract from that, but it will be very similar. But there will be one large oscillation and then on top of that a small oscillation. So you can see the two modes being present when two LC are coupled. Okay. So once again there are a lot of principles that we had in this example, but the important thing was the decoupling that the symmetric matrix orthonormal diagonalization achieved. Thank you very much.